Um, all right, Sabbir, we'll get started with you and I'll let you know if you've really gone over the time limit, but otherwise just, 10 minutes is our general time limit for today. Okay?
Sure, and you guys can see my screen fine.
Yep.
Fine.
Mhm.
Okay, so this talk is titled A Demonstration of Computational Biomedical Knowledge Through the Performance of Ensemble Reasoning. So you guys can think of ensemble reasoning as hybrid reasoning, except we didn't want to use the term hybrid reasoning because in the literature, hybrid reasoning in the semantic web often refers to the combination of A box and T box reasoning. So reasoning over concepts and reasoning over instances. But what we mean by ensemble reasoning is combining different types of reasoning, like abductive reasoning, deduction, induction, temporal reasoning, and so on. So this project really focused on this idea of how can we create a clinical decision support system that reasons in a way similar to how physicians reason. So that goes back to the combination of multiple types of reasoning. So when physicians reason, they don't just do deduction or induction. They combine multiple forms. They abstract the problem out into their background knowledge, and then they uh, deduce a problem and then maybe try to explain it through abduction. And then maybe they have a lot of background information that um, of cases they've seen before, and they found similarities through induction and so on. So a lot of the work in the space focused earlier on clinical decision support systems were single type of reasoning, mostly deduction based. But what we wanted to do was combine multiple types of reasoning. So our use case involved, like I mentioned, reasoning in a way that a clinician is likely to reason. We also wanted we didn't necessarily want to create like a end-to-end production level system. It was more so we wanted to show that show a proof of concept that we were able to demonstrate that multiple forms of reasoning could be integrated and result in clinical recommendations. We also wanted to align with standards, both semantic web standards as well as standards in the domain. So we focused around the area of type 2 diabetes. Mostly that was what our funders were interested in. So in terms of a domain standard, we use the American Diabetes Association guidelines. But we also needed patients that resembled real patients. So we couldn't necessarily use real patients due to things like HIPAA privacy concerns, but we found a training course which described patients with diabetes in different scenarios, which we encoded as personal health knowledge graphs. So again, as I mentioned, the motivation of this work is to create a system that can aid clinicians in reasoning by reasoning how they do. And in order to do so, we took the semantic web approach, or we decided to use tools related to the semantic web. This was mostly because a lot of work in knowledge representation and reasoning has been in the domain of semantic web, and support for deduction is widely advanced already, and there's been ongoing work for support for abduction. And like I mentioned before, this was more of a proof of concept. So we do mention combining a lot of different types of reasoning, like abstraction, abduction, induction. For this scope, we focus mostly on um, deduction and abduction. And abstraction also kind of comes naturally by using semantic web because in the semantic web, you define concepts which are abstractions of real world things. So we designed our own ontology because the existing diabetes ontologies were huge. So deductive reasoning works decent by now on large data, though not maybe not as good as we want for a real-time application. But the current work on abduction reasoning, if the ontology, if the knowledge base is too large, then it's not MP complete yet. So you could be in situations where the program doesn't terminate. So what we did instead was we designed our own modular, smaller ontology just to support abductive reasoning. And yeah, and I mentioned ensemble reasoning earlier, where we're trying to combine multiple forms of reasoning to disseminate domain information and provide recommendations. So in order to combine these multiple forms of reasoning in a clinical setting, we looked to an existing model that has been used in the medical domain. So this model is called the ST model. It is somewhat older model. There has been updates to it. There's advanced ST models now, and there's, I guess, researchers who I guess say that actual reasoning isn't necessarily done using the ST model. There's better models to explain how clinical reasoning is done. However, as kind of like a first pass kind of thing, we thought the ST model was something that we would easily be able to replicate, and then you could imagine this approach would be advanced to more recent models. So the ST model circles around different types of reasoning, and it's like a circular loop where each output of a reasoner or reasoning activity feeds into the next, which actually works pretty well for our case where we're creating reasoning agents. So we can design each reasoning agent as individual modular components, where then the output of a reasoning agent could be used as the input of another reasoning agent. So we use this approach to do therapy planning, differential diagnosis, and plan critiquing. Focusing mostly on therapy planning because we were looking at the ADA guidelines and it had a very clear set of recommendations and rationales for prescribing treatments to patients. So this is a table in the ADA guidelines. It might be kind of hard to read, but on the left, the rows are different treatment categories. Metformin's drug and the others are categories. So SGLT2 inhibitors, GLP-1s, DPP-4s, TZDs, sulfonylureas, and so on. And the columns correspond to factors which contribute to which therapy is recommended. So we pretty much compiled the diabetes factors as well as the therapies included in ADA, as well as certain measurements that we found through our this training course, NetCE, which included different measurements which were used to diagnose the patient and so on. And we use that to create a relatively simple ontology. And then we also represented the NetCE patients as personal health knowledge graphs. So we used an existing ontology, SIO, as well as concepts from FHIR, mostly LOINC concepts and NCIT. And what we did was we included patient attributes, their symptoms, conditions, measurement values, visits, and used that to reason over the patients. So a patient might have certain attributes such as symptoms. They might also have different measurements such as their height, weight, different HbA1c, BMI, different measurements, which can then be used to make inferences. So for example, the HbA1c value of 183 milligram per deciliter is used to infer that the patient has HbA1c in the diabetes range, which is anything greater than 141. And that deductive inference allows us to trigger an abductive rule or an abductive query asking what are some explanations for their diabetes HbA1c to be in this diabetes range. And it could be things like insufficient exercise, high sugar, therapy is not working, or they're not taking the therapy. So in order to do abduction, we used an existing abductive reasoner, which we integrated as a reasoning agent into our clinical decision support system, which was built off of YIS. So this is just a command to the abductive reasoner, which we passed as input to our reasoning agent. So just real quick, it's taking abducibles, which are concepts in the ontology and knowledge graph to limit the scope of the reasoning, just to constrain it further so it doesn't reason over all possible concepts. And then you can provide adapt the ontology, the query. So we're looking at patients for an explanation for why a patient is a diabetes HbA1c level patient. So we built this into YIS, which is a knowledge management framework. And we did some reasoning within YIS using Square, which is not really published. Well, I guess it's published as a pip package, but it's like a in the works reasoning agent we built, which is Sparkle query based reasoning, which we use this approach because it allowed us to easily create custom clinical rules, custom reasoning rules. So we integrated all this into the WISE knowledge management framework. And then we use it to do therapy planning. On the right is some of the outputs to. So I guess we had a patient K who had some aversions and preferences, and based on those, it ranked certain therapies. So it's bigonide, which is metformin, came as the top rank, and then TZD, the GLP-1s, and so on. So we compared these rankings against the ADA guideline rankings to do an evaluation. But this is just what the output looked like, and then you can do display the output or do whatever you want with it. It's a Python dictionary. So what we found was the approach could be applied generally. We did apply it to diabetes, and we did apply it in a clinical setting, but the actual software wasn't domain dependent, and the ontologies we used were domain agnostic. So this approach could be applied in a different domain if needed. We also interviewed a bunch of clinicians regarding their thoughts on our recommendations, and we found that potential users of the system have pre-existing knowledge and factor preferences, which could also then be incorporated, where we only incorporated the factors based on the ADA guidelines. When we gave the output to the clinicians, we included rationales, which was generated from our output, which they found was necessary to build trust in the system. And then overall, we found that a transparent system, such as the one we built, encourages trust, interpretability, traceability, and explainability. So this work was partially funded by IBM as part of the IBM RPI Hales project. And
Great.
that's about it.
Thank you so much, Sabbir. So now we will move on to the next presentation from Eric Mercer, Keith Butler, and team. And we'll save time for questions towards the end. So if you have any, save them in the chat so that you can remember them for later. All right. Okay, great. And it looks like we can see the slides here.
Yes, thank you. Good afternoon, everybody. I'm going to let people read the slides themselves. I'll give a narrative. Model checking won the ACM Turing Award for its capability to prove design correctness of distributed asynchronous systems. It exploits the power of computing to analyze exhaustively every sequence of states that a system can occupy, and then either verifies all of them as correct against a specified property or outputs fold isolation data. Our demo is going to extend model checking to graphical health IT workflows by automatically translating them to and from the languages of formal model checking. Click. Thank you. Human-computer teaming on the cognitive work of healthcare is growing rapidly, but it lacks adequate evaluation methods. And failure risks are too complex to tolerate in and fine for conventional evaluations. We're going to demo model checking on a remote patient monitoring system that's distributed over patients at home, AI in the cloud, and providers in their office. Next. And 2 more, please. Okay, that's great. Thanks. So requirements, well, the knowledge types for HIT design have to be integrated. And the first one that we're talking about is the scenario of the patient's diagnosis and treatment plan. And then there are requirements. And when cognition is being distributed between people and machines, we focused on the cognitive work problem that remote patient monitoring must solve. And you can read that for yourself. It's actionable risk awareness, and we need to define that in a computational way. And then the design is a BPMN workflow for that solves this cognitive work problem by integrating functionality of patients at home, AI in the cloud, and providers in their offices. Next, please. And then you'll get the demos of automatic translations to and from BPMN and Promula, and then the model checking that either proves or disproves the meaning or the correctness of the design. Next, please. One more click. So we assert that the CWP, that the cognitive work problem of remote patient monitoring, is actionable risk awareness. And the space that we're going to show is the computational definition of that. And RPM has to solve this. And it is a finite state diagram. One more click, please. And it has to handle care transitions per the NIH 2019 COVID guidelines. One more click. So you can't quite see at the top there, but there is a space decision that's made. And patients who have comorbidities or are moderate or severe, they're going to go immediately into appropriate ambulatory or clinical or hospital care. The other branch is that the patient will go into appropriate home care if they're pre-symptomatic or mild, or and their severity needs are equal or less than home care. And they'll get orders for home care and vital measurement times and exam schedules and some kind of monitoring. Now, the patient can remain safe in appropriate home care. And after a period of time, they'll get an exam and they'll be discharged if they've recovered. But, next click, they can deteriorate while in home care. And so it's important that there's monitoring that takes place and detects this. Thank you, because there's a direct link into the patient's expiration from being at risk. One more click. So an urgent exam might find that their severity need exceeds home care, and so they'll be ordered into some sort of clinical care, ambulatory, or hospital admission. Or, one more click, the exam might find that they can remain safe in home care with additional prescriptions or more frequent patient monitoring and so on. One more click. There we go. So unfortunately, patients can expire despite the best of attempts at care and monitoring. And the happy path is that the patients all get discharged. Next, please. So this is the RPM workflow that has been certified to solve the cognitive work problem. And it's implemented in the BPMN standard. Now, the design uses pH-ware, a patent-pending technology for a single finger clip to measure and stream 7 vital signs. Now, the top lane models the activities of clinicians. The middle lane, the functions of AI in the cloud, and the bottom lane models home care. The workflow begins up the upper left here with an exam for patients who test positive for COVID-19. And patients that are mild and fit the criteria for home care begin home care down here. With one click, please. Okay, and here's the image of the home care user experience. On the left, there is a finger clip, and on the right is the image of the screen of the smartphone that works together with it. And raw vitals are sensed by the finger clip and sent by the smartphone to the AI cloud. The patient process halts with an exam or fatality, and its process can be restarted after exam is needed. Now, the middle portion is where AI in the cloud has its function. It starts when the raw vitals arrive, and it assigns timestamps and numerical values to the vitals with machine learned algorithms, and then analyzes combinations of time trends. If any combination exceeds preset change threshold, an alert is added, and the process ends when the data and any alerts are sent to the clinician's process up here. One more click, please. Now, this is how the patient panel of the provider gets changed. Any patient with an alert gets migrated up towards the top for priority attention. The data trend behind an alert can be reviewed by the clinicians with one click. Click, please. And there are the data trends. The clinicians maintain decision authority, however, and they may change exam times as they judge appropriate. Now, whenever an exam time is now, one more click then it goes back here for an exam. Oops, too far. Okay, now you can see the complexity of the decision space that the provider's authority has. And that complexity is something that is difficult to say the least. And so we're going to show how you can evaluate this with model checking. Next. One more click. So the proposed solution involves translations. So in order to use the spin model checker here, we have to translate the cognitive work problem from a UML state diagram into linear temporal logic, and the system design in BPMN into the Pramila language for model checking. And so the question is, does it solve it? Next, please. And now we'll go on to Bryce's live demo. It's over to you, Bryce.
Thank you. Okay, so the first thing that happens when I run this script, this is a tool that I created. The first thing that happens is I have downloaded the XML files for the BPMN and the CWP that Keith had explained. And the first thing it does is that automatic translation from those XML files into a set of LTL properties and a Pramila model that's used for the model checking. And here we see each of those models being, or each of those properties being checked sequentially on the model. These properties are verifying various things, such as we're always in during execution, we're always in one of our states in the CWP. We eventually reach one of our goal states in the CWP. And then for each of our states, we verify that the state exists somewhere in our BPMN diagram. And then when we're in that state, we're only in that state and not any other state as well. And then when we leave that state, we take only the allowed transitions out of that state. And those are all the properties that we're looking at. And you can see the majority of them are passing here. We do have some failures. And once the verification finishes, it begins generating counterexample images for the failures. And so while that's, so I'll show what those look like here. They're annotated images of the BPMN and CWP that show the path we take when we hit a failure. So in this case, we're diagnosed with COVID-19. We get examined by the doctor or nurse, and then at this gateway here, we take a turn north towards hospital care, hospital admission. And then we're notified at the top of the image here that this is an invalid state transition. So this is the problem here. We were at a reasonable severity need, and we went to the hospital. So we went to the hospital and we had the wrong at the wrong time, basically. And that happened because there's a typo here where 78 equals home care. It should be outside home care. When we're outside home care, then that's when we need to be admitted to the hospital. But in this universe, it was typed wrong, and so we took a wrong turn here. When we correct that problem here, this is what it looks like. We just changed the label on this edge. And when we rerun verification on the corrected diagram, that's when we get all the properties passed, and that's when we can verify that the BPMN solves the work put forward by the CWP. And now I'll send it back to Keith for.
Oh, that's great, Bryce. Thanks so much. Next slide, please. We'll do this quickly. I know everybody's in a hurry.
Yeah, okay, thanks.
Expected benefits, you can just scan those yourself. Trustworthiness, patient safety, increased quality. And next slide. So here's the FAIR principles that are addressed. Thanks very much. We look forward to your questions after everybody else has spoken.
Yeah, thank you so much for your presentation. And as a note, we will be sending demo slides and of course the recording of this session for everyone, just in case you want to review that later. All right, so I think Dr. Shiell?
Sorry, whenever I share a screen on Zoom, it always closes out the actual menu system that I need to unmute myself. So hopefully everybody can hear me fine. Thank you for coming today. I'm happy to present something that our group at the Ontario Institute of Cancer Research has been working on for quite some time. It's called Overture. I'm going to be talking about kind of what we do as a group and why we do it and how this relates to Overture. And then just give a general high-level technical overview of this open source software that we're starting to promote more outwardly. On the screen here, you have links to our websites. We have overture.bio. We have our GitHub, which we found at overture-stack. And then you have the less interesting email of the man that's presenting to you today. But I'll put this up at the end of the presentation as well, too. And feel free to send me a message if you have any questions. So I just want to start by talking about a little bit about what we do. Everything we do is really centered around data and discovery. A lot of the data that we deal with is clinical data and genomics data. And as a general narrative principle, the individual elements of data are never enough when we want to drive data to discovery. We need to organize and aggregate all of this data. And I have a fun little diagram to show that. In order to gain anything of meaning or value, we first need to aggregate the data. We need to have metadata associated with it. And then only then, with interpretation, are we able to yield new knowledge. So with interpretation, we have new usable knowledge, which is the ultimate goal of all of this data aggregation, is again, that sort of data discovery that we're pushing for. Now, in order to get to this point, we need to have computational tools that mobilize this data, making it widely discoverable, safe, and overall fair. And that's where we come in as the Genome Informatics Group at OICR. We often say here, we're filling the gaps between the genomics data and the researchers who need that data to drive discovery. And now being at MCBK, we're kind of wanting to think about extending that more outwards towards these knowledge bases and knowledge systems that within our organization and outwardly, you guys have been developing and pushing forward. So what does that actually look like in terms of the software that we've built out in the past? So we build discovery platforms. Two seminal projects that we worked on was the ICGC. It's the International Cancer Genome Consortium data portal and the NIH GDC data portal. So these are two large data repositories that store genomics data where researchers can now access them in one single resource in order to fuel their knowledge. And it is essentially the same concept. We have an international audience of data providers that contribute data, and it is all now accessible on a front-end portal. It's clearly a lot of things that go into the back end of that. But as a group, since these two projects, we've expanded outwards quite a bit. We're quite well experienced at building out these collaborative data sharing platforms. So we have the Kids First Data Power Portal, which is pediatric cancer data. We have VirusSeq, which carries viral genomes. I just checked as of before this. It's now carrying 600,000 viral genomes, which is quite an accomplishment for us. We also have ICGC Argo, which is the next advent of ICGC. And what it's doing is it's got quite an ambitious goal. It's analyzing genomes from 100,000 cancer patients, and it's collecting this genomic data alongside all of the high quality clinical data, making it available to the research community in a rapid and responsible way. So this is really providing precision oncology knowledge to the world. So as you can see, we've done this quite a bit. We have quite a bit of experience in building up these platforms. And that's what it really kind of brings us in to Overture. From building up these platforms, we've kind of come to some main core requirements needed in terms of building them out. You need to have metadata management in terms of metadata management service. You want to have a file transfer service in order to get files to and from object storage. You need to index that data in order to make it accessible for both machines and humans. And talking about making that accessible for search, you need a search API. And then finally, as the fifth requirement, you need a portal UI where they can actually access this resource. Now, because of that, what we did is we found we were doing the same things over and over again as a group. So we wanted to reduce these redundant programming efforts and sort of build out a way that we can make these things in a more flexible and scalable manner. And that's where Overture comes into play. So Overture is 5 core microservices that all combine to build into these scalable and flexible genomics data platforms. It's got this orchestral theme to it. We have Song. We'll see this is in line with the requirements that we saw on the previous slide. It handles metadata management. We have Score, which is handling our file transfers. Maestro, which handles indexing. Arranger, which is our search API generator. And then we have Stage, which is our portal UI that you see on the front end. And this was actually developed shortly after and built up on ICGC and the GDC data portals. And we've already implemented it in our own projects, from Kids First to Argo. As a testament to this flexible and modular architecture, we were actually able to build out VirusSeq within a record 4 weeks' time. And based on the demand of that platform, we were able to scale it appropriately, rather seamlessly based on the microservice architecture, to where it now is hosting almost 600,000 viral genomes. Okay. So I just want to give now a bit better of an understanding about how the really central microservices work, and then kind of open up the floor in terms of how you can work with us in terms of using them in your own projects if you're interested. This is all open source software. It's freely available. We have documentation from our website. So if you ever want to spark up a data portal, if you find that there's a use case for you, by all means, we're here to help you guys. I'm going to start by talking about our metadata management services, Song and Score. We essentially have here a data provider on the bottom left corner of the screen who's got data files and has got a metadata file as well too. First thing we want to do is get metadata into a Postgres database that you can see on the right side, and that's where Song comes into play. So in terms of data administration, with Song, you're able to define your own schemas or data models. And then from that, all data providers will have to validate their submissions against that data model, and Song will facilitate that for you. It provides semantic correctness and validation tracking. So it will tell you whether or not you need to update your submission, or if it's all good to go, it will then commit it to the Postgres database, and it will also assign it a global identifier. This is important because when we're using Score now to upload our file data, typically for us in the past, this has been VCFs, FAMs, and CRAMs. However, it's agnostic to all data types. We need to make sure that it's associated with one of those global identifiers. And then that way we know exactly what is in our metadata repository is tracked to files that are located in object storage, creating this sort of rich metadata and rich data repository that can then be used in order to push forward that discovery, making it findable, accessible, interoperable, and reusable ultimately. Now with this setup, this is the most complicated diagram in this whole presentation, so I apologize if that was a lot of information. But the next one being Maestro is a lot simpler. It's taking that metadata repository that we've just created and creating one single Elasticsearch index. What's quite nice about Maestro, and it's kind of a core tenet to our group's work, is that it's able to take distributed nodes of Song databases and create a single Elasticsearch index. So you can imagine a distribution of nodes globally, all converging into one Elasticsearch index where users can then search and query from. Of course, this index is not enough just on its own. Most people aren't interacting directly with Elasticsearch. That's where Arranger comes into play, which is our most flexible tool. It's completely data agnostic. All it needs is an Elasticsearch index. And with that supplied, it will produce a single endpoint GraphQL API. And then from that, it also will link up to a front-end UI components that can then be inserted in your data portal or in your front-end UI. What does this look like? So this is VirusSeek as an example. On the left-hand side, we have a faceted search column, which comes with Arranger. We also have a filter notation at the top of the page, and we have a data table. So as you filter and build out filters, you'll see it populate in the data table below. You can then take the download button and download a manifest in order to get all of the file data and metadata to push forward the discoveries that you want to make. Okay, so now I'm coming to the end of it here. So building with Overture, essentially, that is how Overture works and what we are doing. In terms of extending it out, right now and currently we're mainly involved in data aggregation, but if you have data and you have knowledge and you want to make it discoverable, our tools can help. And ultimately, we do want to hear from you guys in terms of your ideas and find out better ways in terms of meeting your needs. It's quite a flexible piece of software. And we truly believe that it can be extended in all sorts of different creative fashions. And we're looking for as many ways and avenues as we can kind of facilitate that and leverage our software with your work. We're always open to academic collaborations, technical consulting, or mutually beneficial development. And with that, we have a contact page here, but I cannot neglect to thank all the people that are doing all the hard work behind the scenes. The Genome Informatics Group at OICR, creating and promoting the big data tools for those advancing the knowledge and treatment of cancer. And then acknowledging our funding agencies, particularly the ITCR from the National Cancer Institute. Again, thank you very much for listening. That was just at 11 minutes. Hope you guys have a wonderful day, and I'm happy to answer any questions that you have.
And to put together these presentations. We have like 5 minutes before we're going to be put back into the main room. So if anyone has any questions for the presenters, please feel free to ask those now. I think, and by the way, I'm not a content expert here. I'm more just like a staff person that helps out. So I can't say I, super confident in posing any questions. Like I think Harold, I saw that you had mentioned something about
Yeah,
trade-offs.
sure. Yeah, I can answer Harold's question.
Thank you.
So that's true. Certain diabetes treatments are contraindicated when a patient has like high blood pressure or a heart condition or certain kidney diseases or something. So while other diabetes treatments aren't as bad for patients with with these same comorbid conditions. So pretty much we have based on the ADA guidelines, if a treatment, if the patient has a comorbidity like heart disease, then treatments that are contraindicated against heart disease are given a negative weight. In addition to everything else that gets weighted. So things that get weighted are like the effect on weight, on the patient's weight, the cost of the treatment, and these comorbidities against kidney disease or heart disease or certain cases. So pretty much if a patient has a comorbidity like kidney disease, then the treatments that contraindicate those get a negative weight as part of the score, so they're less likely to be recommended.
So the real question is that people have been trying for 35 years on how to take a printed guideline, make it computable, and then have it deal with edge cases and complexity. And so it looks like you have a way of doing that. I worry that a negative score may be too coarse a way of doing it, but that's a separate question.
Yeah, it's definitely a very coarse way, and there's definitely a lot of things we're not considering. But we're primarily doing it based off the guidelines, and then it's just the starting point for someone else to take it to the next step.
Thank you.
And it looks like the breakout rooms are going to be closing in just a few seconds. Thank you so much to everyone for joining today. And we'll just see you in the main room for closing comments and hopefully tomorrow for day 2. Thank you so much.